Hello, this is a presentation for implementation of a BPSK system in MATLAB by Chung Long. This is the final project for EL6509 wireless communication. Um, BPSK, binary shift phase shift keying, is the simplest form of PSK. The carrier frequency and amplitude stays constant while the phase is shifted a certain degree to represent different symbols. The information is stored in the phase of the signal. In binary shift phase shift keying, there are two symbols, 2 and 0, or 1 and 0. When the phase is 0, the binary equivalent will be a logical 1, and when the phase of 180 degrees, the equivalent is logical 0. You can see from this constellation diagram that there's only 2 points, and it represents the two different phases. On the left, you see the time representation of the BPSK. You can see that in 1, when it's a 1, it's a certain phase, and then when it's a 0, it's a certain phase. So in the transitions, you see the phase difference, and you see it shifts right here, right here, right here, right here, and right here. Um, so in this project, we actually simulated in MATLAB. We divided into three separate entities. The transmitter, channel, and the receiver. Each of them had their own separate M file for MATLAB simulation. So here's the BPSK transmitter implementation. Um, there's two separate parts. The first part is the binary data stream. It's we generate a random number in MATLAB and then we encode it with this non-return to zero level encoder. Then that stream is inputted into the product modulator, which transmits into the R frequency. The non-return to zero turns the bit stream between -1 and 1, depending on what the logic is. So if it's a logical 1, then it's a positive 1, and if it's a logical 0, then it's a -1. So that's how the transmitter was implemented in MATLAB. We'll have more details later on the results and what functions we use to generate each individual one of these blocks. The second part that we implemented was the channel implementation. Um, the channel was implemented as a white Gaussian noise along with some attenuation. There was a MATLAB function that we used that was used to add a Gaussian noise to the signal, and then we used a divide function to do attenuation, and then that gets transmitted to this part gets transmitted to the receiver part of the code, the third section of the communication system. So here's the BPSK receiver implementation. At the receiver, we try to recover the original signal. So basically, this is what we get from the channel, and then at the very end is what we try to recover and make sure it's the same as what we transmitted in the transmitter stage. Um, the receiver is first demodulated to go from R frequency to baseband frequency by using a local oscillator. So this local oscillator will be the same frequency, carrier frequency, as what we used in the transmitter section. Um, then we goes to the bandpass filter, which is used to filter out any noise, and then it's fed into the integrated and dump circuit, which is used for a match filter, which is like a match filter. And then we found that from research that the best way to reduce noise and a low pass filter was to use an integrated and dump filter for a BPSK system. We found it was the best for reducing noise. Then the sample and hold stage averages the signal to decide on the result for the binary bit. So basically, it takes multiple samples and then it holds a certain value depending on what's the average of that value is. Um, then the sign stage is the last stage, which we use to decide if it's a logical 0 or 1 from the sample and hold stage. And then this is the last part, which is the recovered signal that we got from the original. Again, and later in this presentation, we'll have the results, which is actually coming up next, which would better explain what we get at what waveform and stuff we get from each section. Here's the transmitter results. from the first section. Um, the code is probably attached in the paper submission and in a zip file. So the top left diagram, it shows the input binary stream that's generated randomly. So in this case, we got a 0, 1, 0, 0, 1, 1, 1, 0, 0, 1. Actually, this is only the first 10 bits. There's actually more, but since we can't plot all the thousands of samples, we only plotted 10. Um, the function we use the function called BPSK mod to transfer the information into the phase of the signal. So it takes the ones and zeros and use it to transfer it to the phase, and then the constellation diagram of that is shown here. As you can see, everything, all the symbols, zeros and ones, are mapped from 0 degrees and 180 degrees phase difference. So that's why there's only 2 points, because it's BPSK. If it's QPSK, you have 4 points, and other there's more with more BPSKs, or more PSKs. The bottom shows the BPSK modulated wave that is sent out the transmitter. It's kind of what we saw in the first or second slide with the phase differences. So when it's a 0 is a certain phase, and then you see the phase shift here when it goes from 0 to 1. So the 0, 1, the 1 has a certain phase, and then at the between here between 2 and 4, there's another phase shift between this slope right here. So then you see the phase difference here, and then from here to here you get the same phase. So every time there's a transition, there's gonna be a phase jump. So this is what's transmitted out of the transmitter, and then that gets sent to the channel that we implemented. So here you see what the signal looks like after going through the channel. The blue is the original signal that we saw on the previous slide, and then the green is the signal after going through the channel with the white Gaussian noise and attenuation. So these are the functions we use. This is to add the white Gaussian noise, and this is to add attenuation. Then that signal gets sent to the receiver that we implemented. So of course we had to do demod from the R frequency to the baseband frequency first, and after the demod is what we get this signal right here. And then the constellation of diagram of the left plot is this. As you can see, you can't really distinguish between a phase of 0 and phase of 180 here, because they're all mixed together. So that's where all the integrate and dump filter and all that stuff comes in play in the next slide. Here is a demod, so you multiply, get the frequency and you bandpass it, so you get the baseband frequency. This is the continuation of the results. The signal, after the signal goes to an integrate and dump filter, this is what you get on the top left. These are the functions we use: integrate and dump, and then the signal, and then this is what we plotted. When we do the constellation diagram, we see that you can see a difference between what we saw before and now with the filter, because now you can actually see that there's two distinguishable different phases. So here there's a 0, and then here's the 180 phase shift. So you can tell which one's a logical 1, which one's log 0. Then we use the PSK demod, which is just like the inverse of the PSK mod that we used in the transmitter. It basically does the reverse of that, and it transfers the information from the phase of the signal to the actual binary bits. Then it's ran through a sine function, which determines if the signal is positive for a logical 1 or a negative for a logical 0. So at the bottom is what you see. That bottom is the actual signal that we cover at the very end, and you can see that it matches what we sent out in the transmitter stage. So then after we see that we can simulate a BPSK communication system, we did some Burr and SNR analysis. We got this code from MathWorks, I think, and then the blue line is the theoretical plot using the formulas for Burr, that we shown in class, and then the simulated one is the one with the triangles, which shows what the burr will be after going through a simulated white Gaussian noise channel. The simulated, you can say they're very similar. So the theoretical and simulated are very similar, and also matches the plot that we saw in class. So burr is usually the the simplest form of modulation, and requires for a certain SNR, it has the least significant bit error rate, so it's the most reliable. But of course, you sacrifice bandwidth for all for the for that reasons. Um, so that's the paper. Um, Thank you, but here we're gonna show the simulation in MATLAB to show how it's run. So here's MATLAB. I have 4 different files. I have the noise. Well, the communication has the receive, transmit, and then the noise. So the noise is a channel, and then the burr function is used for the last part where we plotted the SNR versus the burr. So first you run the TX, and then you let it run. So these figures are going to match what we saw in the presentation. Well, they're different, a little different because the random produces different input streams. So in this case, when I ran it this time, it produces a 110110011 instead of the one before. But you can still see that when you do the PSK mod, there's only 2 variations. There's a phase shift of 0 and 180. And then the last figure is what we saw previously also, which is what you send out the retransmitter. So again, you see the phase change right here at 2, which is what matches here, and so forth. So the same. So then all the variables are saved here, and then the signals ran through the channel, so which is simulated with this noise M file. Um, there's a Gaussian noise and there's attenuation. So then we run this. See, that's what it looks like after the white Gaussian noise is added. You can't really tell the difference between the 0 and a 1. So that's the only thing that plots in the channel. And then in the receive side, you gotta receive, and then you do a debug run. Alright, so again, what we showed in the presentation, you have here green, you have what it looks like without the filter, and then what it was before. And then you have the diagram again of the constellation diagram where you can't see the difference between a 0 and a 1. And then, oops, sorry. And then here you have the demod, or after you take off the R frequency and pick up the baseband, this is what you see. So then you put it through an integrate and hold filter. I'm sorry, integrate and filter, integrate and dump filter. Then you get this, and then you take the constellation diagram of this, and you get the actual 2 different plots, a 0 and a 1. So at the very end, when you convert back from the sample and hold and the sine, you get the original waveform, which is 11011001111. So you get back what you saw in before. So that's the communication system, and then the burrs run like run. Yeah, this is what. So it simulates it plots the theoretical one, which is from formulas, and then a simulated one, which is actually simulating a channel with white Gaussian noise and what it looks like. So you see a little variance here, but that's because it's a little different. But it's very similar, and it matches what we saw in class. That's actually it for my project. Thank you for listening.